The concept that we're going to look at now is prime factorization. So we have prime factorization. Sorry, that's supposed to be an R and an I. So prime factorization. So what prime factorization is, we are going to reduce a number into a composition or a grouping of prime numbers. Well, as we're looking into this, what is a prime number? So a prime number is just that. It's kind of this definition together. A prime number is only divisible, meaning it's going to divide into these numbers. It's only divisible by 1 and itself. So if we look at it, there's only two factors that it can be, itself and 1. And anything times 1 is itself. So basically we end up with, if that's the only value we have, it is considered a prime number. So the way that we do that is we have to figure out, is a number prime or not? And we have a quick little test that we can do it. Some numbers we have are very intuitive if they are prime numbers. For example, 1. It's divisible by 1 and itself, which gives its 1. 1 is a prime number, but it's also, when we divide it, multiply it by 1, we really aren't doing anything. So we're going to kind of ignore that one for the side right now. When we get into the next number, we have 2. 2 is divisible by 1 and 2. There's only two choices that it can be that we could ever have to find this. So prime is 2. 3 is also a prime number, because we have only 3 and only 1 that can be divisible into this number. 4, if we look at it, is not a prime number, because 4 can be divided by 2, which brings it down to another prime number. Next number we have is 5. The only thing that goes into 5 is 5 in itself. 6 is a number that can be divided into 2 and 3 to give each one of those values. 7 is the next prime number, as it gives us the only option of 7 and itself. 8 is a prime number because it can be divided into 2. We would have 2 times 4, and then we could split that 4 up and get 2 times 2 times 2 will give us 8. 9 is going to be 3 and 3, which then goes back down to the primes. 10 is going to be 2 and 5, so it's a combination of these prime numbers. So then the next one we get into is 11. 11 is a prime number because then again, anything below it, it's not going to be able to be divisible by, so all it has is the factors of 1 and 11. So how can we determine that? These ones we kind of know. 1, 2, 3, 5, 7, 11, 13, 17. Those types of numbers, we already have an idea of those basic prime numbers. But how do we tell if it's not a commonly used number, if it's prime or not? Well, there's a simple test that we can do. We can just start running through the values and just start dividing it by whatever we can think of and making it work out and see if, and we can get a lot of values. But if we have the number 616, okay, we need to determine if this one's even prime. Right off the bat, we should know it's not prime because my last digit, my ones place, is even. Because that 6 is even, it is not a prime number, because anything that's even can be divided by 2 and being broken down. So right off the bat, we know that this is not going to be a prime number, and we can work that down and factor it out. Okay. So what about if we take a bigger number? So we'll come back to this one and break it down in a little bit. But what if we have the number 2029, for example? Is 2029 a prime number? Well, first off, we know right off the bat that it's not even because our last digit is a 9. So that's our first clue that we have to at least check it. So the steps to figure out if a number is prime or not is twofold. Number one, Step number 1, we take the square root of the number that we're looking for. Okay, so first thing we do is take the square root of 2029. We'll go square root of 2029. So that means when we plug that in, that gives us an answer of 45.044. So we're just going to bump that up to 46, just because there's change and we want all those values to be included. So now we're going to look at every prime number that is less than 46. And then we're going to check it against this 2029 to see if it hits. So coming back with 46, the values that we have that are prime under it is 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 20, let's see, 24 is not prime, 25 is not, 26 is not, 27 is prime, 28 is, 29, I believe is not prime. And then we go into 31, and then we go to 37, then we go to 39, I believe. I'm just going to kind of cheat real quick and look that up there and make sure I got these right. So I got, oh, I did make a mistake. Coming back down here, 27 is not a prime number. 27 is divisible, which I should know. That makes 9, so it's a divisible by 9 number. So I apologize. So 1, 2, 3, 5, 7, 11, 13, 17, 19, 23 and 29, 31, 37, and then we have 41 and 43, and then the next prime number is 47, which is bigger than our number. So then we got to go back and look. Okay, what are my easy values that I can start looking at for this? Well, I know we're going to discount 1 because 1's in everything. 2 is going to go into our 2029, or looking if it can go into it. And we know it can't because it's not even. So 2029 is already taken off. And then we just can go through and start looking at all of our different combinations to see if they divide out. So we're going to take 2029 and we're going to divide it by each prime that we found over here. So we take our 2029, and this way we're not just plugging and chugging with every value we can think of. We get down to kind of a simple set of them. So 2029 divided by 23 is going to give us a value with a decimal, so that's not it. We'll go divide that by 5. That should be out because we know right off the bat this doesn't end in 5 or 0, so 5 is gone. So we don't even have to do that step. 7 is going to be 289 and change, so there's a decimal on it. So 7 doesn't work. 11 is 184 and a decimal. Then we look at 13 is 156 and a decimal, so 13 is, so it can't be divisible by 13. Divisible by 17 gives us 119 and a decimal, so that's not it. 19 is 106.789, which gives us the decimal, so that's not it. 23 gives us 88 and change, so that's still not good. 29 gives us 69.965, which we have a decimal, so it can't be divisible by 29. We jump up into 31, we get 64 and a decimal. 37 gives us 54 and a decimal. 41 gives us 49.487, so it's got a decimal, so that one's out. And then our last one to check is 43, which then gives us 47 and a decimal. So just running real quick through those calculations, taking the 2029 and dividing it by every one of these primes less than the square root of our original value, we have come to find out that not one of these gives us a whole number, which is also the definition of our prime number. It has to be a whole number. So given that this test here, every single one of these numbers failed by giving us a decimal, this means 2029 has to be a prime number because none of the primes below its square root, are going to be able to give it any kind of value. So 2029 is prime. Because again, dividing by each of these values, these other primes that we were looking at, gives us a decimal, doesn't go into it evenly. So then we can quickly assume, hey, this is prime, we're good, we can leave it at that. Now, in this program, obviously, and as you're doing these math problems, you're going to start recognizing these patterns, you're going to start figuring out which ones can go into it, and that's all we're looking for is, can we break this number down? Now, do you have to always go after the biggest number by itself? No. Take the easy routes. Find the low-level value numbers that you can subtract out of this. Find what works for you and solve for it. This is just a quick and dirty test, quick being a relative term, to be able to figure out if a number is prime or not. All right, so let's come back to this 616 value that we were looking at. So 616 we determined is not prime, and it can be factored down. So let's take a look and dig into that number a little bit more. So we take our 616. Now we want to split this out, and we want to use the easiest methods that we have. Because it's even, we know right off of the bat it's going to be divisible by 2. So we take 616 and we divide it by 2. And we're going to break this out. Now this method that I'm using to break these numbers out, it's called tree factorization. There's another one that you can do with just like prime factors and putting them in boxes. They basically do the same thing. We are just looking to see how these numbers split up and what do we multiply them back by each other to come back to these previous values. So 616, we're going to divide it by 2. And when we do that, we have 308 remaining. Now, I can take that 308 and I can split it up because I know 308 is not prime because it's even. So my first test is if it's even or not, then we have to check some other things. So 308, we divide that by 2, and that gives us 154. Same process. 154 is even, so therefore I know right off the bat we can pull a 2 out of it. So 154 divided by 2 is going to break me down into 2 times 77 to get back to that 154 value. So now, as I'm looking at it, I come down to a value. 77 is not even, so therefore it is not divisible by 2. So now we have to check, is there anything else that'll go into 77? Well, one of the easiest ones that we have right off the bat is when we know that we have an ordered number, a pair of numbers, 77, 66, 35, 33, or whatever it is. That is going to be broken down into 7 times 11. And then I can go through and look. Well, 7 I know is a prime number, so I'm done with that branch. I can't go any farther with it. 11 is also prime. And so now that I've broken all of this down, every single one of my numbers is now broken down into a prime value. So 616 is going to break down into all of these factors multiplied together. So I get 2 times 2, so there's the second one, times 2, which is the third one, times 7 times 11. So there is my prime factorization of the number 616. Now, when we go to record and report these numbers into the computer programs, and just kind of as a general reference, we want to order these numbers from smallest to greatest. So our 2's are going to go on the left, and then the bigger numbers are going to follow in numerical order from left to right. So in the end, the correct way to write this is 2 times 2 times 2 times 7 times 11. Mathematically, it would still be correct if we put something down like 7 times 2 times 11 times 2 times 2. That is technically and mathematically correct, but how we want to put it in a standard form follows this trend, is we want to go lowest numbers on the left, larger numbers on the right. All right, so that's basically the gist of prime factorization. How can I get this value into a smaller term? Okay, let's look at one more example. If I take 4,058, and I want to break it into its prime factors. So first thing is, it is even, so I'm going to divide it by 2. And that's going to give me 2029. Well, like we looked earlier, I'll scroll up to it, we found out that the number 229 is a prime number, so therefore, when it comes to this 4058, 2029 is as far down as it can go, and so therefore, the prime factors of 4058 is just simply 2 times 2029. And we want to put that in proper form. So we get the prime factors of 4058 is 2 and 2029. And then once we break those down, we can get to see how these are going to work for us later. Now, one of the ideas behind this, and why do we use prime factorization? Because it is a little bit of work to list out all of the factors. Sometimes we don't have to go down to prime factorizations, but we can. We can get down to these base numbers of each of these sets. With that being said, one of the reasons that we use prime factorization is we can use it in reducing fractions. So as we talked about in the multiplication and division videos, as we're going through and solving them, if we can break a number up into its components, what makes up that number, and as I'm doing a fraction, I can then use that to simplify the fraction. If I have a factor that's on top and bottom, I can pull that factor out of both of those numbers and reduce the number down as we go. So, for example, if I'm looking at a problem and I have the number 99 out of 11. So if I'm going to go through and start multiplying this equation, or this is my answer, whatever it is, I want to reduce this to its lowest value to make it simpler and easier on me later on. So I have to look at these values and see what can I take out of both the top and the bottom, keeping it mathematically equal. So 99, I know, is going to break down into 2 values. Several different values, honestly, if you want. I could break it up into divisibles of 3. I could break it into divisibles of 9. I could do divisibles of 11. Whatever it is, there's multiple ways to break this down. But the way that I want to break it down is going to be based on what do I want to get rid of. So down here on my denominator, 11 is a prime number and therefore cannot be broken down any farther. So if I can get this term of 99 into a term of an 11, or a grouping of an 11, then I can eliminate it. So 99, if we look at it in terms of an 11, then I can break that down into 11 times 9. And then my denominator is going to just stay at 11 because we don't break it down into anything because it's already prime. My 11s then cancel, and so then I'm left with my answer of just simply 9 or 9 over 1. Either way, both of those are correct, but this, moving over to here, the 9 is our simplified version of 9 over 1. And we can kind of connect those two together as much as we need it. All right, let's look at another example. If I have 99 over 165, I need to be able to reduce this down. Well, I don't think 165 is divisible by 11, so we'll check that. 165 divided by 11 is going to give us 15. Well, that doesn't really help us out here, but we can kind of, break it apart. So 165 is going to break up into 11 times 15. Now we know that the 99 is going to split up to 11 times 9. And that actually did kind of help us a little bit. Okay? because now we've got an 11 on top, 11 on bottom, so those are going to cancel each other out. Then I'm going to look, what does this 9 split up into? The 9 is going to split up into a 3 times 3. My 15 is going to split up into a 5 times 3. And so therefore, now I have a 3 on top, 3 on bottom with multiplication and division only. Those 3's, top and bottom, are going to cancel, leaving one 3 on the top and one 5 on the bottom. And so my answer is going to reduce from 99 over 165 to simply 3 over 5. Now in the electronics world, we do have a lot of values that are going to combine together, and then eventually something of those is going to fall out, and we're going to remove some of those to get out deliberately and make our life easier. And we're going to have factors and values and all sorts of stuff that just come in and out of these just long enough to get us through an equation, and then they fall out later on. And we'll talk about some of those as they come up. But that's the idea behind reducing fractions. So we're going to reduce fractions, and if we have to go far enough into the prime factors, we can. We can also take any number out of these. So if we had these two numbers here, we could have taken out, instead of an 11 and a 3 separately, we could have taken a 33 out of both of these numbers and still ended up with this value. So we don't necessarily have to take it down to prime factors. We just have to find common values that are both in the numerator and the denominator, and then when they're multiplied by each other in that fraction, then they can cancel out. So that's one of the ideas behind prime factorization, is it helps me reduce these values and make it easier to see where these are going to end up.